Good evening, good afternoon, and good morning to everybody out there. I'm told we have people from all over the world with us this evening. Welcome to our Rose-Hulman chat. I'm Mario Simoni, and I'm the department head for electrical and computer engineering. And in about a half hour, we'll be switching places with our department head of physics, optical engineering, and nano engineering. So I'm told that we have people out there with interests in many different disciplines. So I'm assuming that you want to get to know a little bit more about electrical and computer engineering, and that's what I'm here to tell you about. We have an opportunity for you to submit questions throughout the chat. So if you come up with a question, please go ahead and put it in the chat. We will only have time to answer a few of those questions, but we'll try to get through as many as we can. If we don't get through your question, our contact information will be in there. I am happy, more than happy, to answer questions over email that you would have about electrical and computer engineering, the majors, the way we teach. If you have more general admissions questions, those will be answered by our admissions staff. So without further ado, we'll go ahead and get started. So many people who express some interest in electrical and computer engineering, they have a strong background in mathematics and science, and they know they want to do some form of engineering. They may have had some experience with robotics in high school or with tinkering around with hardware like Arduinos, but they don't have a full breadth of the opportunities available to you with a degree in electrical or computer engineering. And so the field is so broad. I like to use the analogy of medicine. So if you are wanting to become a physician, there is a huge difference between a pediatrician and a heart surgeon, and the types of problems you're going to solve, the types of people you're going to help, and the opportunities available to you. And so we have that kind of breadth in electrical and computer engineering as well. So I'd like to just cover that breadth for you, and then we'll be happy to take some questions and go down the questions list. So I'm going to take electrical and computer engineering and break it up into a number of subdisciplines. And the first subdiscipline is electronics and circuit design. And so if you take any piece of consumer electronics and you open it up, could be your desktop if you've built a computer, or your phone or remote control, anything these days. You open it up and you look inside and you see these green or red boards, plastic boards that have a bunch of electronic parts and pieces on them. And all those parts and pieces have to be selected and they have to be connected. And we have to figure out which parts and pieces are needed for that particular application. The parts and pieces that go into a DVD player, for example, or your Alexa or your Siri, can be very different than the parts and pieces that go into an electric automobile, right? So knowing which pieces to select and how they get connected to perform that task is what we call electronic design. This is kind of a foundation for electrical and computer engineering because anytime you want to do anything with electricity, to do work, to solve a problem using electricity, you have to apply these same principles to that problem. So as you get more advanced in those principles, you can do something called integrated circuit design. And so if you look on those same boards, you'll see a bunch of tiny little black squares, and they'll have a bunch of little pins coming out all the sides, and those are called integrated circuits. And so the design of those integrated circuits is a little bit more complicated because it's like taking one of those whole boards and shrinking it into an itty bitty package, and then encapsulating it in plastic so you can't get access to it, and then putting pins connected to certain parts of that circuit on the inside. So that design's a little bit more complicated, so you have to get to more advanced levels to be able to do that. But there's tons of opportunity in electronic and integrated circuit design. You may have heard of the CHIPS Act, which is bringing a lot of semiconductor fabrication back to the United States. So there's a lot of opportunity there. The next area is machines and power. So this is power generation and distribution. Everything from the power plant over there to those high voltage transmission lines that go all across our country, to the substations. When they come into a big substation, you see behind those fences, and you have all that big heavy power equipment behind that fence. And then how you're going to distribute that to the local area, or maybe to industry, to a factory. So it turns out that wiring up a factory is not quite the same as wiring up your house, and there has to be a lot more considerations for all that high powered stuff. And then these days, with the national power grid, we're trying to make energy more sustainable. So we're including things like wind and solar. But when you do that, that creates complications in the grid. And so we have to think carefully about how to integrate those. So there's a lot of opportunity and design challenges there. With last spring, even if we were talking about the national power grid, the biggest challenge to providing enough power to the national power grid was charging stations for electric vehicles. We were going to replace all the gas stations with charging stations for electric vehicles. So that's a huge amount of power load, a change in the power load to the power grid. But today, if you ask me today, what's the biggest challenge to the national power grid? It's not electric vehicles anymore. It's AI data centers. And so those of you who are my age out there that are watching, you might remember 3 Mile Island in Pennsylvania and New York area was a nuclear plant that they had a meltdown back in the 80s. It wasn't as bad as Chernobyl. It was nothing that big, but it did shut down the plant shortly thereafter. Well, an AI company recently bought, from my understanding of the news, recently bought 3 Mile Island and is going to bring that nuclear plant back online in order to power an AI data center for the Northeast up there. So there's significant changes in the challenges facing our power grid and our power stability and security. So lots of interesting problems to solve there. The next area is control system design. So in control system design, we are trying to control the behavior of a system. So I like to use cruise control, right? So we provide an input that is the set point. So I tell my car to go 70 miles an hour down the highway. Now things happen and the speed doesn't stay at 70. Maybe it goes below, starts to dip below 70. Well, how does that control system respond to get the speed back up? Well, it has to take in inputs, like it has to monitor how hard the engine is working, has to know how fast the car is actually going. These days we have adaptive cruise control, so it has to know how far in front the car in front of me is, right? So it has to take in all this information, and then the only thing it can change about the car is how much gas to give, right? So if you look down at the gas pedal while cruise control is working, you can see that gas pedal going back and forth kind of subtly in order to keep that speed back at 70 miles per hour, right? Well, these days, all that control system, taking in the inputs and changing the amount of gas, that's all done by a computer, right? And computers run on software. And so let's say I wanted to write the software for this control system, but I'm a novice software developer. So I want to write this program to be really simple. So anytime I go below 70 miles per hour, just floor the gas, right? Give it everything you got. Okay, well, what's going to happen? You're going to jump up in speed. You're going to go above 70 miles. Now I'm above 70 miles. Well, how do I write a really simple program to slow me down again? Well, take off the gas and slam on the brake. Okay, well, that's going to get you back down below 70, right? So it turns out a control system like that will work. It will keep your speed, your average speed, around 70 miles per hour. It's going to be a bumpy ride though, right? So this is an example of what we mean by a bang-bang controller. I'm just banging back and forth between two extremes. Now, for something like an automobile, that's much too simple. But if we look at a different kind of control system, like your thermostat in your house, that operates that way. It either turns on the furnace or it turns off the furnace. It doesn't turn the furnace on a little bit. It just either on or off. Your air conditioner is on or off, right? Based on your temperature difference. So when we talk about something as complicated as an automobile, though, we need a lot more complexity in that control system design to be able to take in all those inputs and do a lot of mathematical computation on that, using some complicated algorithms to figure out how much gas to give. And that's why you see that gas pedal going back and forth really subtly, right? But this is one way that AI and machine learning is becoming an important part of electrical and computer engineering. Because if I'm going down a straight and flat road through central Nevada, which I have done, and I know how straight and flat those roads are, okay? And it's a sunny day. It's always sunny in central Nevada. So that's an easy program to write to make that car stay at 70 miles per hour. But if I'm going up and down the mountains and it's snowing or raining and I've got cars all around me, those conditions are changing on a second by second basis. And that's where I need something like AI and machine learning to adapt on the fly so that I can find the right pattern for controlling my system in the presence of all these distractors, right? That's one of the important ways that we use AI and machine learning. Okay, so the next area is digital system design. And so this is the design of all the hardware that your software is running on. So it turns out all that software that those computer science guys are writing, those are all text files. So it's no different than writing a book. So really, writing software code is like writing a book. The computer has to turn that text into actual ones and zeros that will turn on and off switches in the hardware that's running that program. And that's what we mean by running a program. And so we have to understand as electrical and computer engineers, we're the ones that design that hardware, right? What I think is really interesting about the digital design is the complexity of these systems. So last spring, NVIDIA is a company that makes graphics processors for your computers. And now those processors are being used to compute artificial intelligence. And so they announced a new processor with 200 billion switches in one tiny little package, right? 200 billion devices. So this would be like, imagine I handed you 200 billion $1 bills. And I asked you to take all of those $1 bills and stack them up in the shape of downtown Manhattan, right? So you would have to lay each one of them out and organize it. That's an incredible amount of complexity there. And as you're going through that, you have to look at each one of those dollar bills and figure out if there's a tear or a mark or damage to any of them that would invalidate that bill. And if one of those 200 billion dollar bills is invalidated, you got to throw out all 200 billion and start over again. That thing is garbage, okay? So incredible amounts of complexity there and organizing it and figuring out what we even need to do with all those devices to do the job that we need it to do, right? So interesting problems and challenges there. Next area is electromagnetics, and there's two parts to electromagnetics. So one is that we use electromagnetic energy to do things. So every time you take out your cell phone and you send a text or do anything with Wi-Fi or Bluetooth, anything wirelessly that phone is connected to, that's an electromagnetic wave that is traveling from your phone to the destination or from the destination back to your phone. And that electromagnetic wave, it carries that information, right? So we know how to generate a wave in a pond. We take a big rock and we throw it into the pond, and you see the waves ripple out from where that rock hit the water, right? Well, that electromagnetic wave travels in the same way, just like those waves on the surface of the pond. But we have to do it using electromagnetism, right? So we have to design antennas, and we have to know how those antennas are going to work with that electromagnetic energy, okay? The other aspect of that is material properties, so related to electromagnetic energy. So if I take my phone out here in this office, I might get 4 or 5 bars. But if I walk around the corner, not too far from here, and get in an elevator, I got 0 bars, right? So what is it? I'm not that much farther from the tower that I'm losing the signal. It's because the elevator is made out of a big metal box, right? So what is it about metal that blocks that electromagnetic wave? But all the building materials around here, the brick, the drywall, the trees that are outside, right? All of that stuff, the glass in the windows, that doesn't block the electromagnetic wave. Well, it's because of the material properties. And then if you look at something like a medical imaging system, like a CT scanner, an MRI scanner, MRI stands for magnetic resonance imaging, right? So you have electromagnetism there, okay? So, and you look at those electromagnetic waves going through the body and how they interact with all the different tissues and how we use those interactions to image the inside of the body. So incredibly interesting problems and challenges to solve there, right? Okay, so the next area then is signal and image processing. Okay, so signal processing. So I like to use Alexa or Siri as an example for this. So when you use Alexa or Siri, you say, hello Siri, or hello Google, or hello Alexa, and then it starts doing something, right? Well, when I'm talking, that's a sound pressure wave. If you've taken physics, you know that sound is nothing but pressure waves, mechanical energy bouncing back and forth between the air molecules, right? Well, if I talk at my phone or at Alexa or Siri, that's an electrical system. So mechanical energy hitting an electrical system is like throwing a rock throwing a rock at your Alexa. It's not going to do anything, right? So the first thing we have to do is turn that mechanical energy into electrical energy. And we do that with the microphone. It's the job of the microphone. So coming out of the microphone now is a voltage, what we call a voltage. And that voltage is squiggling. You know, it's going up and down, it's vibrating up and down the same way that my voice vibrates. So it gives me now an electrical energy that's proportional to my vocal vibrations, okay? But when we talk about Siri and Alexa, these are computing devices. They run on software. So somewhere in Alexa and Siri, it's actually looking for the text HELLOSIRI as if I had typed it into Siri. All right. Well, these vibrations and these squiggles, they may be electrical energy, but they're sure as heck not text, right? So as electrical engineers, we have to process this speech signal and turn it into a form that we need to make our system work. And so this is an example of what we mean by signal processing. So this would be speech to text processing, right? Image processing is just another form of signal processing. Imagine a medical image and you're looking for where's the tumor in that image, right? So you're taking this signal, which is an image, and processing it to figure out the location of the tumor in that image. So it's the same kind of mathematics and the same kind of algorithms, and there's software involved in this. This is another area where AI and machine learning is important to the future of ECE technology. Because if I'm sitting here in a quiet room, Regina's being really quiet, but if she was talking, right, there'd be all kinds of extra noise coming in here. But if I'm in a quiet room with just me and Siri and there's no distractions, no noise, right, I can write software to do that speech to text processing really well. But if I got a mouthful of food, if I'm angry or excited, if I sing it, right, I still want Siri to respond in the same way, but those squiggles that respond to my voice, those are going to be really different, right? So we have to extract those patterns even in the presence of time-changing conditions, and that's where AI and machine learning can be helpful, okay? So next area, embedded system design, all right? So embedded systems are computing devices, but very small computing devices that we can put into application-specific situations. So that's a big word. What does that mean? So I may not need 200 billion switches to do something like this Fitbit, right? Maybe I get by with a few 100,000 or something, okay? But this Fitbit is a computer. It has a computer processor inside of it. It is running software, but it's a different kind of computer than your laptop or your desktop or a big server farm, okay? This computer, it simply listens to the same inputs over and over. Every few milliseconds or microseconds, it's checking for those same inputs. It's looking at my pulse. It's looking to see if I tap, okay? And then it's responding in the same way. It's counting my pulses, lights up the screen when I tap, okay? So it's just listening and responding. And this is an example of what we mean by an embedded computer. If you look in an automobile these days, there are hundreds of these embedded computers within one automobile. They're in your tires, they're in your steering wheel, they're in your seat belts, they're in the entertainment system, all throughout the engine and all the different sensors in the engine. And all those miniature computers have to be talking together and sharing information with the main central control unit of that vehicle. And so you have this network of computers that all have to work together. And that's one of the challenges in modern embedded computing systems. And so you may have heard of Internet of Things or smart technology, right? That's all embedded systems technology and design. So lots of interesting challenges there. And that's really where we're seeing a lot of the impact on our day-to-day lives, is with that smart technology that keeps coming out. Okay, one more area, and that's communication systems. And so in a communication system, I'm trying to get information from here over to here, okay? But in order to get there, it's got to go through something called the channel. So let's say you're trying to send a text to your mom or dad or a friend, right? So your phone is the transmitter. That's over here. That's the one sending the information. And the other person's phone is the receiver. Now let's think about what's in that channel now. So when it leaves your phone and you hit go, it's got to go through the airwaves to the tower. It's got to go down the tower. God knows where it goes, through the internet. And then it's got to find the tower where that other person is. My sister's in Italy right now. If I called my sister just using her normal phone, it's going to go all the way to Italy to get her, right? So it's got to figure that out and go there. And that's got to go up that tower, out the airwaves, and then to that other phone. So all of that stuff from phone to phone is what we call the channel. And if we think about how many things can go wrong with that transmission, and yet they don't. We just hit go, and the other person receives that just like less than a second later, or maybe a second later, right? So all that's designed intentionally. So if you think about a cell phone tower in downtown Manhattan, right, or a big city, you got thousands of users on that tower at any given point in time. So at no time do you have to sit there and look at your phone and go, wait a minute, I'm 354th in line, so I got to wait 10 minutes to send my text. You just send your text and it goes, right? And when you send it, it doesn't block anybody else, and it doesn't go to the wrong phone. Any information request doesn't go to somebody else's phone, right? As you're moving around Manhattan, you don't ever have to sit there and say, wait a minute, I'm switching cell phone towers. You got to send the information over here now, right? It just knows where you are and it adapts accordingly. So all that's designed intentionally into that kind of a communication system. And then, these days now, everything is a 5G phone, 5G phone, 5G phone. Got to have a 5G phone. Well, 5G turned out to be a bit of a bust from what they were promising. So it didn't quite perform as well as they initially expected it would or could. So now they're already talking about 6G technology that's coming out, and they're trying to define 6G communication systems. They're going to have even more people on a certain cell phone tower and get more data even faster than you can now, right? So interesting challenges to solve to make that happen, okay? Now, if you were to go to a school other than Rose-Hulman, usually these are big state schools like Purdue or Georgia Tech. They would have a couple of additional areas in electrical and computer engineering. So one of those is optics and photonics. And so that is like the fiber optic internet that people are getting to their homes these days. What that means is that the information is carried by a light signal through a very thin filament of glass or plastic, okay? And so there are many advantages of using light, but we still have to get from a computer that's electrical into light and then transmit using light through the long cables. And then when it gets to the other end, we got to get back to electrical signal to get it into the computers again and the digital systems, right? So that's what we mean by optics and photonics, is this combination of light and electricity. We have that here at Rose-Hulman. It's just not in the electrical and computer engineering department. And fortunately, in, I don't know, a few minutes, you're going to hear from the department head of the optical engineering degree program. So we have a whole degree in optical engineering. Those courses are still accessible to you with an electrical and computer engineering degree. We just don't have them fully contained within our department, right? The other area is semiconductor devices and fabrication. So Let's say you wanted to create a solar panel, which is made out of semiconductors, okay? And that's what the CHIPS Act is about, and all those semiconductor manufacturing companies coming back to the US, right? So if you wanted to make a solar panel that was more efficient, so with the same amount of light, you got more electrical energy out of it. Well, you need new devices to be able to do that. Someone's got to design those devices and figure out how to build them into a larger system. That's a lot of what electrical and computer engineers do. So again, that is not contained within electrical and computer engineering, but you're going to hear in a few minutes from the department head of the nano engineering program. So we have a whole degree in that. And those courses are also accessible to you with an electrical and computer engineering degree. Okay. So that gives you an overview of all the opportunities available to you with electrical and computer engineering. As I said, it's a very broad discipline. Now, modern problems involve people from all of those sub-disciplines to work together. So, and we give you, through our curriculum, we give you a foundation in all of those areas. So whether you're taking electrical or computer engineering, you will be exposed to all of that, okay, as a required part of the degree. And then as a senior, you get to pick a few more advanced courses that focus on one or just a couple of those specific disciplines, right? And that's how then you would specialize, okay? So with that being said, now I think that covers the overview. I'll go ahead and take a few questions.
Mm-hmm. So the first question that we have is from Aiden. Does your department have a specific area it focuses on more? And it sounds like we are pretty broad, but I don't know if we have a specialty area.
So we have expertise in our department. In fact, I'm not quite sure I understand the whole question, so I'm going to try and answer. But we have faculty with expertise in all of those disciplines. So we provide advanced courses in all of those disciplines. So I'm not sure if that answers your question, but I hope it does.
I think so, yes, because again, it's just, is there a specific area that we focus on more? And it sounds like we can cover it all.
Yeah, we can do most of it. Yep.
Okay. Now our next question, could you speak a little more on electrical engineering? Could I, as a double E student, combine a few of the computer engineering, I'm assuming courses, rather than focus entirely on the ECE major?
Right. So we have 2 degrees in the department: electrical engineering and computer engineering. Okay. And so, excuse me, through the sophomore year, both of the programs have the same foundation. Okay. So you're going to be taking courses. Electrical and computer engineers are going to be all mixed up and jumbled up in the same courses through pretty much the spring term of the sophomore year. There's like one course that's different between the 2 programs up to that point. After that point, they both differentiate and they start to take different courses, right? And that's where you see the differences. And so right now there's about 6 to 7, 8 courses that are different between the 2 programs, okay? Some of it is a math and science background. That's why I say 6 to 8 courses. And then when you specialize in those senior electives, the computer engineering students are much more adept at getting into also computer science courses for some of those advanced courses. So there's an opportunity to get more software in there, right? We are exploring an option. Right now, you can't do both degrees, right? But we're exploring some options where potentially in the future, you could get a major in electrical engineering, say with a minor in computer engineering. So you would have to take those extra 6 to 8 courses in computer engineering to do that. But we haven't nailed that down yet. So I don't want to make any promises, but it's something we're considering.
Yeah. And for time, I think we have time for one more question, but it'll be kind of big. Are there opportunities to develop your own projects? And then I'm going to add, could you maybe speak on maybe some internship or co-op experience that some of our students have had?
Yeah, we love projects in our department. So about 80% of our courses in our curriculum And that's just the required courses. So many of if you go to electives and those advanced courses, you could go up even higher. But 80% of our required courses have a hands-on laboratory component to them. So we do a lot of hands-on. Now, when I say incorporated into the course, I mean you will meet 3 days a week for a regular class, 1 hour class. And with that same professor, you'll meet 1 day a week for a 3 hour hands-on laboratory with that same faculty member. And we have faculty members teaching the labs, not TAs, not graduate students, and it's all an integrated part of that course. So if something comes up in the class that they want you to see in the lab, it's all very tightly coupled together, right? So that's one part. Then there are opportunities to do independent study projects with faculty, and there are research opportunities with faculty. And we also have a design track. The design track consists of a freshman design course, a junior design course, and then a senior capstone that's a year-long design course, okay? In those design courses, they're more problem-based learning. So for example, in the freshman course, the first half of the course, we're talking about how to do basic software and how to wire up components to a miniature computer like this. And then that's the first half of the quarter. The second half, you're working with a team to design a robot with sensors to make the robot perform a number of complicated tasks in a competition. And that's a team-based project. We tell you what the competition is, but we don't tell you how to build the robot. That's what you got to figure out how to do, given what we taught you in the beginning part, right? And then the year-long capstone project is a project that you're working to solve a problem, because ultimately engineering is about solving problems. So you're solving a real-world problem for a client in that whole year, right? You get a team and a project at the beginning of the year, and you work on that all year long. And those projects come from industry, they come from faculty research, they come from nonprofits, from alumni. But you're working for somebody else, right? And then with internships and co-ops, we don't have a required co-op program like some schools, like University of Cincinnati is one that comes to mind that has a required co-op program. But about 95% of our students do an internship or co-op. And what we call an internship is you're just gone for the summer quarter, right? You don't need to take classes in the summer if you keep up with your normal curriculum, okay, to still graduate in 4 years. So the summers are kind of open. So a lot of people go off and get an internship during that summer term. The other thing you can do is a co-op. And when we say a co-op, we mean you're gone one of the three main academic terms in the year, like the spring and the summer. So you're gone for 6 months, or the summer and the fall. We have a lot of students that do those too. Usually these days, a lot of students are coming in with some AP credit, or maybe they take a course between their freshman and sophomore year over the summer. And what that does is that opens up slots. If you've got 4 courses worth of credit, you've got a whole term where you don't have to be here on campus, and it's still not going to delay your 4-year graduation. So that gives you an opportunity to do that 6-month co-op, or do a study abroad, or get an extra minor, or do all kinds of things with those what I call holes in your curriculum there. Yeah.
Excellent. We've hit our time.
Yeah, I'm sure I talk long and fast.
It's
so.
wonderful information though, but I provided the guests on our chat here with your contact information if they have additional questions after tonight. But thank you so much for coming and talking about your department.
Thank you all for being here this evening. We're very passionate about what we do, and we hope we get to see you on campus sometime in the near future.